Okay, so this is the set of lectures for week 2. We have 4 lectures in reasonably small chunks where I want to talk about fundamentals of experimental design. And I'm going to start with the aims of the class, as always, which is that I want to introduce some of the constraints that are imposed by the scanner. So to really sort of emphasize the point that you can have your very favorite psychological paradigms, but it's exceptionally rare that you could take one of them and just put it in the scanner and have it work. The constraints that the scanner imposes, both in terms of the environment and in terms of the physiology, the measure that we're actually doing, mean that we normally need to adapt our paradigms in order to make them work properly in an fMR scanner. I'm then going to introduce blocked and event-related designs in 2 different lectures, and then, or videos, excuse me. And then with an emphasis of highlighting where they're good and where they're bad and how you can use them, as well as talking about how they can be combined to sort of take advantage of the strengths of both. And then finally, the last 2 videos in this week's series are going to talk about sort of design considerations, particularly around how to choose the right baseline and why baseline really matters, but also ways of avoiding bias, because there are a number of ways that it can creep into an fMRI experiment that are different than some other experiments. And of course, they're the standard old sources of bias that we need to think about too. So that's the material I'd like to cover this week. It's going to be done in 4 short videos, and the first one is going to really start talking about the constraints imposed by the scanning environment and how that then leads us to block designs. So there are 2 sets of things that are really important, right? One is the physical environment, the fact that you're in an MRI machine, which is a very strange environment. You're lying on your back. There's all sorts of physical constraints here associated with it. And then there are also physiological constraints related to the fact that what we're measuring, our dependent measure in this case, is that BOLD signal, the blood oxygen level dependent signal. And that's going to impose certain restrictions on the way we actually design our experiments. And both of these together mean that whatever your favorite experiment type is, your particular psychological design that you enjoy, you just can't just take that and then put it in a scanner and expect it to work. You're not going to get meaningful results out of that. I want you to understand why that is and what you need to do to make those changes so that you can design your own experiments to work properly in an MRI machine. So the physical constraints that we're talking about are things like the fact that you're in a very, very strong magnetic field. There's a small space, it's physically a constrained area. As I mentioned in the first week's lectures, it's also a very loud environment due to the Lorentz forces of the magnets on magnets producing sounds. And people are lying on their backs. So for all these reasons, it's a very different environment than what we normally deal with in psych experiments, for instance. And what this means is, some equipment won't work. So for instance, if you just want to collect reaction times to button press boxes, you need special button press boxes that work in a magnetic field like this. They exist, and our scanner, as well as most other MRI centers, have them, but it's specialized kit that you need to be aware of. Similarly, if you have something that you want to do that's a little bit different, like you need to use a trackball or something else, you can't just take the equipment and bring it to an MRI machine. 1, it probably won't work in the magnetic field, and 2, it could be quite possibly extremely dangerous for the subjects for a variety of reasons. And those are things that we've covered in week 1's MRI safety training. Plus, there's a very limited range for equipment. You're literally lying in a tube. Depending on the scanner and your size, you may find that your shoulders are actually physically touching the sides of the scanner. So there just isn't a lot of room for a lot of extra kit around there. It means that there's also a very limited range of motion, right? You can't get people physically doing big movements. Like, for instance, if you're interested in gait and how people walk, it's a very, very hard thing to study in a scanner because, first of all, they're on their back. Second of all, there's no room for them to move. And third of all, you couldn't even put in some sort of Stairmaster kind of approach because the magnetic field doesn't allow it. One of the consequences of that is that in some cases you have to deal with claustrophobia as well. So for some participants, the reduced space is very claustrophobic and it can completely change the way they interact with their environment. Now, we do a lot of things to try to deal with that, and I talk about that a little bit in our safety training, and I'll show a video of how you actually set this up in the scanner so that you can see these things. But nonetheless, it's something that's always in the back of your head. You need to think about whether or not the environment is just producing an anxiety state for your participant. For those of you who are really interested in vision, there's very limited peripheral vision just based on the fact that you're in a tube and there's just so much space to be used there. So for instance, John Greenwood in our department does a lot of cool work on clutter in the periphery, and those things are relatively hard to do in a scanner simply because there's just not a huge amount of visual periphery to look at when you're in a tube like that. As I mentioned in week 1, there's difficulty with hearing simply due to the fact that it's very loud, right? If there's always scanner noise going on and you're interested in sort of audio psychophysics, well, how do you differentiate the sounds that you want to use as stimuli from the sounds the scanner is actually producing? And in week 3, when we talk about sort of advanced experimental designs, we will talk about ways of trying to do that, but it's a challenge and you need to bear it in mind. And then the other thing is just lying on your back in this kind of a state, particularly if there's anxiety, can be uncomfortable and it can cause fatigue, right? So that is to say that an experiment that would be perfectly fine in the lab where people are sitting up in front of a computer and can move freely and be happy might work perfectly well for 40, 50 minutes. Whereas 40 or 50 minutes in a scanner doing the experiment might be just very unreasonable due to fatigue. So for all these reasons, you do need to think about the physical constraints imposed by being in an MRI suite. But the much more fundamental concerns are about the physiological constraints, right? So we talked about the fact that the hemodynamic response function, the HRF, is very slow because it's dependent on the blood flow changing. So despite the fact that neuronal activity is changing very rapidly on the order of milliseconds or at least tens of milliseconds, the hemodynamic response, the blood flow and the bold signal are changing on the order of seconds. So it takes 4 to 6 seconds for there to be a peak response in the blood flow in response to an increase in neuronal activity. And then it might take 20, 21 seconds for it to return down to baseline levels. So what you get is a very complicated time series data because as you run events, all of these events are kind of blurring together in time. So you don't have sort of discrete individual things that happen. Very much unlike reaction times. You have a trial, somebody responds, and that response is independent of the trial before it and independent of the trial after it. That's just not true in fMRI. The bold signal that we're measuring is a continuous time series and it's going to need to be treated that way. The other thing that's important to think about here is the sort of size of the signals. So in this image, I'm showing 2 scans, 2 sections from a person, one of which shows a very significant activation and one of which doesn't. I'm assuming that you can't see the difference, and it probably doesn't even help that much if I sort of point out that this is where the activation is. The reason is that the bold signal changes tend to be small. I mean, a 1% bold signal change is a whopping big MRI effect. A lot of what we're looking at is sort of 0.3 to 1% of a bold signal change. So what happens is we have these data in this time series, so we're acquiring these data, say, every 2 or 3 seconds, and we're looking for these reasonably small changes that are occurring over time. And we have a model of what our experiment is like. So in this particular case, this would be something like that Peter Bandettini experiment from week 1, where at 10 seconds in, somebody starts tapping their fingers, and it goes for 20 seconds, and then they stop. And then 20 seconds later, they start tapping again. So this is an example of a block design in the sense that the person is doing a task in little blocks. 20-second blocks on, 20 seconds of block with nothing happening, or rest. Now, that's all well and good, so we have some expectation about when we should see these effects. But we then have to take into account the fact that what we're measuring is that bold signal, and it's not instantaneous. It's actually delayed and blurred. So what we're really looking for is an evoked hemodynamic response function, shown here in the top plot, that smooths these blocks out according to what we know about the nature of the physiology, right? The hemodynamic response function. And that gives us a model where you can see where you've got blocks of task happening, you've got blocks of rest happening, and what's important is that this is a relative measure, right? So the numbers that you get out of bold, the absolute values, are absolutely meaningless, right? What's important is the change from the sort of position where there was a task happening to when there was no task happening. That relative difference, that relative change, is the signal that we're most interested in. And as I said, this tends to be relatively small. It tends to be somewhere between about 0.3 and 1% signal change in the data. Now, what that means is that the larger we can make the difference between the on and the off response, the easier it is to detect it, right? So sensitivity to actual activation depends on maximizing this relative change. And that is what leads us into this idea of block designs. So what I'm showing here is the expected hemodynamic response to blocks of tasks that last different amounts. So for instance, on the far left, we have a simple task that only lasts for 1 second, and you can see it evokes a relatively small and rapid hemodynamic response function. Something that's 5 seconds gives you something quite a bit higher, but also still fairly rapid. And by the time you get to 20 seconds, the height that it's evoking doesn't change. All that's different now is how long the stable period is in that block. So in other words, you can see that at 1 second you get a small change, at 5 seconds you get a larger change, at 10 seconds it's larger still, but not as much. And then by the time you get to 20 plus seconds, it doesn't change anymore. The height of that evoked response is the same. What that means then is that as long as we use blocks that are, it turns out, 16 seconds or longer, we're maximizing the difference between the on condition and the off condition. So we're increasing the size of the effect to be as large as possible, and therefore improving our sensitivity to detecting it, right? Now, the reason that we don't just have one long block of task followed by one long block of rest is because of problems with noise. So anytime you're measuring anything, what you're measuring is a combination of the signal that's of interest and sources of noise. And you want to try to maximize signal relative to noise so that it's not, for instance, swamped. And this is very much one of the issues that we face with FMR. So one of the properties of noise in a scanner is that there tends to be a very low frequency component, almost a linear component. So for instance, what you often see is that the noise signals will increase fairly dramatically over time, or they'll decrease fairly steadily over time. And if that's the case, then the reason that you don't want one long block of task and one long block of rest is because it's very heavily confounded with noise, right? So in the example shown here, there's more noise in the on part of the experiment than there is in the off part of the experiment, and that's going to exaggerate the difference, but incorrectly. It's a false positive in that sense, okay? But you don't know. It could have gone the opposite direction, in which case you'd get something that was actually a false negative. So it's important that when we design our experiments, we take into account this difference between signal and noise in a way that makes it sensible. And one way to do that is to use multiple short blocks, right? So in this case, you can see that the experiment's going, here it's going on and then off and then on and then off. But each of these on blocks have different amounts of noise in them. And each of these off blocks have different amounts of noise in them. On average, when you combine them, it's going to end up being equal amounts of noise in the on and the off block, so that when you compare them, when you look for those relative changes, the noise essentially cancels out. So the advantage to a multiple short block experiment is that you improve the signal to noise ratio, not by changing the signal, but by decreasing the effect of the noise. It turns out that you can actually sort of compute what would be the most optimal way of doing that based on the hemodynamic response function. And what you can find is that there's a period here in the black line where you gain the most power, most sensitivity to the actual signal effect, whereas the red line is showing the most influence of noise. So what you want to do is look for the area where the black line is highest while the red line is lowest. And it turns out that that falls within 16 to 45 seconds. Okay, so what we're saying there is block lengths that are between 16 and 45 seconds are optimal for detecting signal and reducing noise, or reducing the influence of noise in your experiment. And that's exactly why, when you look at lots of these blocked experiments, the block lengths tend to be in that range. A 30-second block length is probably the prototypical block design in FMR. But there's nothing better about 30 seconds than 16 seconds or from 45 seconds. Once they get a little bit longer than 45 seconds, you can see that there's a rapid increase in the amount of noise, the red here. So now there's the difference between the signal and the noise is decreasing fairly dramatically. So longer blocks are less advantageous by a lot. So if you can keep it to 16 to 45 seconds, you're definitely in that optimum window. Okay, so with a block design, the main advantage is that it's maximally efficient, right? It increases the signal to noise ratio, meaning that the effects that you're measuring are as large as possible, which increases your sensitivity. You need less data to collect good, solid results, to avoid false positives and to avoid false negatives. Now, there are other things that come with it that are also beneficial, including the fact that it reduces task switching. So for instance, if you have two things going on and you want people to alternate from one to another, then there are cognitive costs associated with that. If they only happen about once every 45 seconds or something, that's not so bad. Whereas if they're happening for each trial once a second, then a lot of the signal that you're measuring isn't about what the person's doing in terms of processing condition A versus condition B. It's all about the task switching that they're doing. So a secondary advantage of a block design is the fact that it reduces these task switching costs. Another advantage is that it's less sensitive to stimulus rates. So it's not sensitive, right? It's still sensitive to stimulus rates. However, if you have trials that are happening once a second or once every 2 seconds, that makes less of a difference in a block design than it does in an event-related design, which the second video will talk about in a lot more depth. So there is a greater flexibility in the way you design the specifics of the trials that you're using in your experiment in a block design. And then the final advantage, which seems pretty trivial but perhaps makes a big difference in practice, is that block designs are relatively easy to analyze. Like, it takes a lot less time and effort to analyze a block design and know whether or not you're getting good results than it does to analyze an event-related or a mixed design. Now, theoretically, they're very similar to one another. In practice, it's just that one's easier to do than the other. So this is a final advantage, to block designs. Now, the downside to using a block design is that they encourage things like strategies and expectancies. If you know that for the next 45 seconds nothing's going to change and you're always doing the same task, then maybe you don't have to focus on it that much. So there are whole experiments for which that would be really critical. So for instance, if you're doing a go, no-go task, these are experiments that are about these rare events, no-go events, and that's what's interesting. So what you're trying to do is figure out how people suppress patterns that they've decided that they've made very common, they've habituated to. So what happens in a go, no-go experiment is typically you see a string of letters and you're told, anytime you see a letter, press this button, except if it's an X. If it's an X, don't press the button. That's a no-go event. Okay. So what happens is you see a string of letters and you get used to it, A, B, M, Q, R, S, and you just tap the button and tap the button and you get used to it, but then an X comes up and it's hard to not tap the button, but that's your job. By definition, that has to be a rare event. You can't have 45 seconds of X's because you stop paying any attention. You're not suppressing it at that point. You're just not paying attention at all. So in that case, an expectation or a strategy completely changes the cognitive nature of the task. So for things where you have rare events, a block design is a bad choice. And there are lots of experiments like that. Priming experiments are like that. There's any time that you care about whether or not somebody gets the answer right or wrong, where you want to divide out, correct from incorrect trials because you may assume that there are different cognitive processes involved, etc. Those are by definition rare events that you can't plan for, and therefore they'd be difficult to do in a block design. You also just can't detect transient events. If what you're really interested in is something that's happening very rapidly, well, by definition, that's not what a block design is. You're only studying things that are happening somewhere in that 16 to 45 second window, not rapid transitions. And then this is a little bit less common, but it's important in FMR. Sometimes what people are interested in is also detecting the empirically determined hemodynamic shape in an individual in a region of the brain. So I've given you sort of a standard default canonical fMRI hemodynamic response function in all of my plots, and in fact I'm going to do that throughout the course. But it does vary from person to person. It varies from place to place within the brain. And sometimes it's really useful to have that information. if that's something that you're interested in, if you're interested in that kind of a neurophysiological question about the nature of the blood flow and how it varies from place to place, then a block design is a very bad way to do it. You need rapid changes so that you can measure the specific shape. The whole point of a block is that we get away from the specific shape of the HRF and get a sustained on versus a sustained off. Okay, so those are the information about block design, where it comes from and why it's useful. I think that block designs sometimes get a little bit of a bad rep because they are immensely useful, but their simplicity sometimes leads people to think that it's maybe not the best way to go forward. I think that it's really important to consider very carefully sensitivity issues. If you can get away with using a block design that maximizes the signal to noise, then you absolutely should. It's a very, very sensible thing to do. And it means that you're going to have to collect significantly less data than if you have to look for a smaller signal or a larger, a signal in a larger noise component.